good to see so many people out, and I hope that we can have a wonderful session of 6 lectures dealing with climate change. Could I have the first slide, Dave? This is a quote from an editorial in the Hampton Spectator this past Wednesday. If you believe public opinion research, climate change and the environment matter most to an increasing number of people. That isn't surprising, since we are seeing the real-life effects of climate change happening around us. A growing increase in violent weather events, like the one that devastated the Bahamas and left a huge cleanup in Canada's maritime provinces. Fires, flooding, human displacement on a historic scale. The remains are shrinking rump of deniers, but more and more they are being drowned out by reality.
Put a T before the R.
Yes, thank you. Yeah. Society is becoming more and more aware of the impact of climate change. I've been teaching about climate change as professor of chemistry at Redeemer since the late 1980s. And as we look at the history of the whole thing in one of the later lectures, we'll see that we've known about this for well over a century. We're finally getting to the point that I think we are ready to act. Our politicians just need a bit more of a push. This series of talks is sponsored by our church, this Education Committee, but World Renew, next slide, and the Office of Social Justice have also been actively involved in promoting this and in just helping me as well in terms of some ideas for putting it together. And I want to thank them, and they have a display up in the back, and you're welcome to drop by there after the session tonight and just talk to Cindy or Maria from World Renew. The Office of Social Justice also sponsors the Climate Witness Project, of which I am a regional coordinator. Our task is to implement some of the recommendations from the 2012 report on creation stewardship that was passed by our synod right here in Ancaster at Redeemer College. And so we are a group under the Office of Social Justice. We have representatives around North America, and our goal is to, first of all, educate the members of churches. It's to also provide resources for worship services so we can focus on creation care in our worship. It is also to provide ideas on energy conservation as one of the practical aspects of this. And lastly, also to advocate for change. And we'll talk more about that in some of these other things at a later time. So let me begin then with our discussion on climate change tonight. Okay. Fossil fuels have provided us with an unprecedented living standard. They've been around since, or in usual to say, since about the 1700s, with the discovery of coal that could be used for operating steam engines. Next. And it's been the main driver for our standard of living. We've all enjoyed the benefits of fossil fuels. I suspect that most of us got here tonight using fossil fuels. We heat our homes like fossil fuels. Some of the electricity we use in the room here is generated from fossil fuels. So there's a lot of good things that have come from that. But there is a downside. Whenever any fossil fuel is burned, the carbon dioxide that is emitted through the burning process is emitted into the atmosphere as a byproduct. Next. And the net effect then is that the stored carbon that was in the ground is converted into heat energy of some form, but the waste carbon that results from that in the form of carbon dioxide goes up into the atmosphere. An average automobile releases roughly 5 to 6 tons of carbon dioxide annually. And when you think that we have over 1 billion cars in the world, that's a lot of carbon dioxide. And we have, used carbon or fossil fuels for so many other things. Next slide. When we look at the graph of world energy consumption, you notice that the graph really starts to shoot up where the arrow is. What happened there historically? Not the Industrial Revolution.
The end of the Second World War and increasing.
The end of the Second World War. And with all the industrialization that took place, especially during the Second World War, to produce the airplanes and the tanks and everything else, the factories after 1945 didn't want to shut down. So what else can we make? Automobiles, of course, have been manufactured already with Henry Ford's assembly line, and that industry then recovered and grew and took over a lot of the factories that were being used for producing war machinery. And then you can see that it rises very rapidly after that. Now, you can also say, well, that's probably because the population of the world has increased significantly. So let's look at the per capita energy consumption. And this is on the average amount of energy that is being used worldwide. So you take the total amount of energy, and how they calculate all that, I'm not so sure, but there are people that can sort of at least make a rough guess of that, divided by the population, and this is what you end up with. Notice the huge amount of fossil fuel that we use per capita. It's the major source of fuel. And you notice that since about the 1940s, we've almost doubled our per capita use of energy. That's doubling it in a matter of 60, 70 years. What are we using it all for? Do we need so much? We need to ask ourselves some of those questions. Next. We can also look up data on the energy use per capita. And there's information pretty much for every country in the world. Canada does pretty good. We're right near the top. There are a few countries that use more than Canada on a per capita basis, but their population is also a lot smaller. But Canada is one of the highest in terms of per capita energy. Notice that Germany is about half. Is their lifestyle that much worse than ours?
Cold winters.
No. Sweden has cold winters, and they're somewhere here as well. The UK is, only 3,000 units, whereas we're at 7,500. Now, this also includes, of course, all the manufacturing and all the resource extraction. This is a per capita for Canada. Next. So what happens to all of the extra carbon dioxide that we add to the atmosphere? Well, some of it actually will be reabsorbed into the biosphere. Some of it gets dissolved in the oceans and other bodies of water, but the vast majority stays in the atmosphere. So roughly half stays in the atmosphere. Now, if it's in the atmosphere, we should be able to measure it. The next slide. And in fact, this is a graph often referred to as the, get the name now, whatever, special curve, Keeling curve. In 1957, Charles Keeling developed a method for measuring carbon dioxide on a daily basis. And he set up a measuring station in Hawaii, well out into the Pacific Ocean, far away from any industrial area, so that you wouldn't be influenced by the emissions from local industries. And you notice that it goes up and down. Well, that's because of these seasonal changes. Hawaii is in the northern hemisphere, and so during the winter, plants are not photosynthesizing and releasing, or taking in carbon dioxide and releasing oxygen. So during the winter months, the carbon dioxide levels go up. Come spring, they start to go down until at about this time of the year, they'll have reached the minimum again for that cycle and start going up again. But what do you notice about the shape of that curve? It keeps on increasing. And from last year to this winter, the last two peaks that you see there is about 3 parts per million. Now, what do we mean by parts per million? That's a unit that's often used for measuring carbon dioxide. It means that if I have 1 million molecules, 400 of them would be carbon dioxide, if it's 400 parts per million. So, 1 part per million is 1 out of 1 million molecules. So 400 parts per million would be 400 molecules of carbon dioxide for every 1 million molecules of air. Our current level is, or the highest peak there, is roughly 412 parts per million. So that's the highest we've reached. Well, do we have any idea what the levels were like before this time? See? What we see, this is the concentration for the past 1,000 years, and the different colors that you see here are based on different researchers using different methods to assess the carbon dioxide levels from that time period. Some of them use ice cores, some of them can use tree rings, so there's a number of different ways that can be used. But you notice that since the year 1000, it's been pretty steady up until the 1800s. And then we start using coal, and we start seeing the levels going up. So it certainly tracks very closely to our use of fossil fuels. Next slide. So what are then some of the effects? One of them is, of course, atmospheric warming and climate change itself, which is going to be the focus for this series. It also affects plant growth, and I'll refer to that in one of the subsequent talks a little bit. And then also the ocean acidity is actually changing because of carbon dioxide. And associated with all that, we also have the air pollution that's associated with burning fossil fuels. Next. So how does carbon dioxide affect the temperature of the atmosphere? Well, we have to understand that the energy that comes from the sun is a form of radiant energy, radiation. And it's made up primarily of ultraviolet light, visible light, and infrared light. Or we call it UV and IR and visible radiation. Diatomic molecules, of which the atmosphere is primarily composed, nitrogen and oxygen. In chemistry, you write them as N2 for nitrogen and O2 for oxygen. That's an oxygen molecule and a nitrogen molecule, which make up about 75%, or the nitrogen makes up about 78% of the atmosphere, oxygen 21%, and 1% of other gases, of which the main one is argon. Carbon dioxide doesn't even make this list. So diatomic molecules are not able to absorb the energy that's coming from the sun, and so the energy passes right through. The UV is absorbed by the ozone, which is up in the stratosphere. And that ozone is O3 instead of O2. It's not a triatomic molecule, it's a triatomic molecule. And so it is capable of absorbing UV, and that actually removes much of the UV in the sun's radiation before it strikes the Earth. If it wasn't there, then the UV would quickly damage plant tissue and animal tissue and lead to a lot of problems. So, next. So to maintain an energy balance, we have sun's energy coming in, but we also have energy going back out again. Because otherwise, if it only comes in, then it would get warmer and warmer and warmer here on Earth. And so the Earth has to have another way of getting rid of that extra energy. And it does that in the form of thermal radiation, or long-wave infrared radiation. As you are sitting here, you're all emitting infrared radiation, whether you like it or not. You are emitting it. And I can actually measure it with one of these thermometers. It's a thermometer that can measure the radiation that reaches the sensor and translate that into a temperature. So Bob, if you just put out your hand, 36 degrees. You've got warm hands today. Okay, and you can point at the floor, and it gives you the temperature of 23 degrees. So this is able to measure the incoming long-wave infrared radiation and convert that to a temperature scale based on something in science called a black body emitter, or black body radiation. Next. Some of the gases that are out, or the radiation that's going out, can be trapped by non-diatomic molecules, such as carbon dioxide, water, and these are known as greenhouse gases, discovered already in 1861. So these greenhouse gases are able to absorb some of the outgoing radiation, and when that molecule absorbs the radiation, it can do several things. It can start to vibrate faster. It can also re-emit that radiation in all different directions. And it can also transfer that energy to neighboring molecules. And from your grade 9 or 8 science, you might recall that temperature It's really a measure of molecular motion. If we get molecules to move faster, we say that the temperature is higher. If molecules slow down, the temperature is cooler. Okay, so when these greenhouse gases absorb the radiation, they then get more energy, causing them to vibrate more, which then causes warming. Right? So this is one way then in which that energy is dissipated in the atmosphere. The vast majority goes straight out into space, but a small amount of it is trapped. Next. And it's really the presence of these gases, these greenhouse gases, that is God's provision for keeping the Earth at a suitable temperature. Venus and the other planets don't have this kind of an atmosphere, and their temperatures can be very extreme. Our temperatures are controlled, they're regulated through these greenhouse gases. Okay? And so here you see a sort of a schematic of what's happening. It's a bit of a complicated diagram, and we have the incoming solar radiation. Some of it's absorbed by the Earth, some of it's scattered by particles in the atmosphere, clouds, for example. The Earth, in turn, emits the long-wave radiation, some of which is absorbed by clouds, water vapor, and the greenhouse gases then, in which case it can be emitted back in all different directions or vibrated more. Next. So, when the concentration of any of the greenhouse gases changes then, we're changing the balance between the incoming and outgoing radiation. And this is kind of the key behind climate change. If we have more greenhouse gases in the atmosphere, less of the energy ends up going into space. It actually stays in the atmosphere or gets reflected back to the Earth. Which then means that eventually it's going to get warmer in both the atmosphere and Earth. Any questions? So the result is that we have then a warmer temperature in the atmosphere, which then in turn keeps the Earth slightly warmer, like adding a blanket or like being inside a greenhouse. A greenhouse does somewhat the same thing. The solar radiation comes in, but the outgoing long-wave radiation is trapped by the glass or plastic, depending on what surface is being used. Okay, next. This is a graph that shows the changes in the average Earth temperature over a number of years relative to the average for the whole of the last century, from 1900 to 2000, basically. They've taken the average of all the temperatures, plotted them. If it's lower than the average, you see the blue. If it's warmer than the average, you see the red. And I think you can see a definite trend here. But the last number of years have certainly been well above average, consistently, for quite a long period, since around the mid-1970s or so. It's been gradually warming up. And as you know from some of the reports this past summer, we've had some of the hottest July months on record, especially in Europe, where 40 degrees was not unheard of this past summer. And other parts of the world are also suffering from very high temperatures. Next. Oh, yeah, Dick.
What caused the sudden spike in the 40s?
What causes the sudden spike in the 40s? It's related in part to the jet stream. And I'll talk about that a little bit later on. Because the jet stream also controls where the winds will flow. The spike in the high temperature was caused by the warm air from the Sahara driving north across the Mediterranean into southern Europe. And that had to do with the movement of the jet stream. Okay, I know it's not a very detailed explanation, but it is related in part to that. Next. This is data that's been obtained by satellites. So satellites also have the ability of measuring the temperature of the Earth using similar devices as this thermometer, a little bit more sophisticated. And these are different satellites that have been used here. And you can see that they all trend pretty close to each other, considering that they're going over different parts of the Earth. But they show again a consistent increase in the average temperature of the Earth. Next. Is that temperature uniform? No. So this is just a graph of temperature data taken, and this one was on February 2017. Again, done using satellite information. And these temperatures are measured with respect to a 1981 to 2010 baseline. So again, that becomes the average, that base. And when it's darker red, like here and here, that means that the temperature is well above what it used to be. And when we have the blue, it's below. It's at a lower temperature. So some regions are cooler, and some are significantly hotter. But what's the overall trend when you look at it again? They all look pretty much above average, on average. But specifically, it doesn't mean that every place on Earth is going to get warmer. I think that's the point that scientists want to make. Not every region on Earth will get warmer. Some will get much warmer and also experience things like drought, whereas others will experience cooler climates and perhaps more rain. Conrad? Oh, this is for a specific time, a specific date. Yeah, this is in February. So, in other words, in February, this area would normally be cold, but it's warmer than it normally was. And you can look at the graphs for all kinds of regions available. There's so much information. You have to kind of pick and choose a little bit to show some examples. Not necessarily. Not necessarily. Because it varies seasonally as well. Next. So, what are the common greenhouse gases? Carbon dioxide is not the only one. In fact, water vapor is probably the most common and most abundant of all the greenhouse gases. But it is a greenhouse gas. It's one of these triatomic molecules. Diatomic molecules, remember, cannot serve as greenhouse gases. Nitrous oxide, methane, carbon dioxide, and some of the freons. And I'll say more about each of those in turn. Next. So what are then some of the sources of the greenhouse gases? Well, a major one, of course, is combustion of fossil fuels. And I should mention, of course, that carbon dioxide naturally cycles through creation. When things decay, carbon dioxide is emitted. As we're sitting here, we're giving off carbon dioxide. That, of course, is a natural process for any living organism. What we're talking about here is taking the stored carbon, fossil fuel, and combusting it. So we're adding extra carbon dioxide to the carbon cycle. In 2017, 36.6 gigatons, and giga is 1 billion. So that was the amount for the whole world. This year, or this past year, we don't have the data for this year in yet, 37.1. So it's about a 2% increase in the amount of carbon dioxide emissions from fossil fuel. It's going in the wrong direction. We really need to get that number down. But it's been increasing steadily, as we also saw in one of the earlier graphs with the use of fossil fuels. This data, the amount of greenhouse gas, tracks the use of fossil fuel very closely. Cement is another major source of carbon dioxide emissions. And what happens in making cement, we take calcium carbonate, which is also limestone, and when we heat that up, we decompose it at about 1,000 degrees Celsius. We can decompose it, and the carbon dioxide is driven off, and calcium oxide is left behind as a powder. The calcium oxide becomes a major ingredient of Portland cement. And it's the component of cement that actually makes everything stick together and hard. About 8% of total anthropogenic or man-made emissions comes from this source. So it's not insignificant. And look at all the cement buildings that we have and the concrete that we use. All of those, in addition to the fossil fuels required to heat them up, also emit a lot of carbon dioxide. This question, Sean?
That's a good question. The cement, which is calcium oxide, when it's made cement, then it's harder. Will it react with the carbon dioxide in the air?
It does some, but not totally. So it's not like 100% absorption again. So there is some that is absorbed. You're right. And there are some rocks, and we'll talk about that shortly, but we'll just leave it now. Deforestation. The way that was done in the early years when this area was settled was done simply by burning all the wood. The bigger trees were logged, and then all the small stuff was burned. And all that stored carbon that was in those trees ends up going into the atmosphere again. That's happening right now in Brazil with all the fires. And the forest fires that we've seen in BC and California and Alberta and so on. They also cause quite an emission of carbon dioxide. That is not a form of fossil carbon dioxide, but it still contributes to the overall carbon dioxide level unless there's enough photosynthetic activity to take in an equal amount of carbon dioxide from the atmosphere. But a farmer's field does not take in as much carbon dioxide as a forest does. And a farmer's field cannot store carbon very well. whereas a forest can store vast amounts of carbon. And then wildfires as well. Yes.
That first point there, from 2018 data and 2017, you said it's at about a 2%. Do you have other data that shows, like, has that slowed as we've made improvements into combustible engines and so on? Have you seen that slowing, or is that just a steady increase?
It's still increasing significantly. And it doesn't look like it's going to stop unless we change some major policies. Next. Nitrous oxide is another greenhouse gas. Some of that is produced naturally. So when you have a lightning storm, it will produce some nitrous oxide. And that nitrous oxide actually serves as a nutrient for plants. It's God's way of providing nitrogen for forests. So during a thunderstorm, the electrical discharges cause oxygen and nitrogen to combine. One of the products is nitrous oxide. There are several other oxides of nitrogen that can be formed simultaneously, but one of them is nitrous oxide. Agriculture also is responsible for a fairly high amount of nitrous oxide, because when you put excess nitrates on the land, there are bacteria that will denitrify the nitrates, in other words, decompose them, and one of the byproducts of decomposition is nitrogen, or the nitrous oxide. So agriculture is another source. Also, whenever we burn a fossil fuel at high temperatures, like a lightning discharge, the high temperatures in an internal combustion engine can also cause nitrogen and oxygen to react with each other to form nitrous oxide. That often leads to air pollution. And back in 1976 or so, we started putting in catalytic converters to minimize the emissions of nitrogen oxides. One of the other oxides of nitrogen is nitrogen dioxide. And that actually is a brown gas. And sometimes in the summer, when you drive into Hamilton, you see kind of a brown color in the atmosphere. That's due to the nitrogen dioxide. Nitrous oxide is just NO. Nitrogen dioxide is NO2. And there are a bunch of other oxides of nitrogen. Aircraft also will emit the nitrous oxide because they're again burning jet fuel at high temperatures in the engines, which then also causes oxygen and nitrogen to combine. Biomass burning. So whenever you have the high temperatures, you can get oxygen and nitrogen to combine with each other. And then any type of fire, of course, delivered or a wildfire can also form that. Next. Another greenhouse gas that is actually increasing in some ways are the high halocarbons or the freons. You've probably all heard of the term freon. What's it used for? Air conditioning equipment. So they have been widely used as solvents in the chemical industry and as refrigerants. The CFCs contain only chlorine, fluorine, and carbon. So hence we call them the chlorofluorocarbons. These were discovered back in the 1920s and discovered to be also very good refrigerants. And after the Second World War, when air conditioning became more popular, it became more widely used, it ended up causing the major problem in the ozone. It was responsible for the breakdown of the ozone hole that you might recall from the 1980s. In 1987, the Montreal Protocol was an international agreement to phase out the use of the CFCs, the chlorofluorocarbons. And then they were replaced by hydrofluorocarbons, in which there's no chlorine anymore, but we now add a hydrogen atom to the molecule, and adding a hydrogen atom to the molecule enables the natural processes within creation to break the molecule down somewhat. And it's also to be phased out, because, as we'll see shortly, it's also a very powerful greenhouse gas. Next. So, a summary then of some of the greenhouse gases. Carbon dioxide, and somehow my program got mistranslated here. But there are headings here. This is the greenhouse, this is the formula, the time that it lasts in the atmosphere, and this is the global warming potential. And a global warming potential is a measure of how much of this infrared, long-wave infrared radiation that's going out into space can be absorbed by a single molecule of the gas. Okay, so the global warming potential of carbon dioxide is given a value of 1. Methane is about 28 to 36 times as powerful. And it depends on how you measure this. These numbers are based on a 100-year average. So taking into consideration, suppose these gases last in the atmosphere for 100 years, and not all of them do, what is the impact that they would have in terms of acting as a greenhouse gas? Nitrous oxide can stay in the atmosphere roughly 100 years, and it is around, or close to 300 times as powerful as a greenhouse gas compared to carbon dioxide. So one molecule of nitrous oxide is equivalent to roughly 300 molecules of carbon dioxide in terms of being able to absorb energy. And that has to do with the chemical structure of the compounds. And then the freons, and there's a whole range of them, but the global warming potential goes from anywhere from about 100 to a high of 23,000, depending on which of the freons you are working with. There's a whole slew of them, and I don't want to get into all the chemistry of them. The take-home message, I guess, is they're not good for the atmosphere. Whatever they are, we don't want them in the atmosphere. Next. So, what about some of the changes then in the levels? Well, we've already seen carbon dioxide. So this is the graph from Mauna Loa in Hawaii, the Keeling curve. The next one represents the amount of nitrous oxide. And you can see that there's a pretty steady increase in its concentration. Now, the amount is not as high. It's in the part per billion range. But nevertheless, it's still significant because it has such a great global warming potential, almost 300 times as much as the carbon dioxide molecule. Methane, for a while, was leveling off nicely, and since, the late part of the last decade, it's been starting to increase steadily again. So we see that it's also on the increase. And then here are 4 of the common freons. This is one of the chlorofluorocarbons. This is another one. And this is the hydrofluorofluorocarbon, which have also been banned. And this is the hydrofluorocarbon. The hydrochlorofluorocarbons were in use for a short time. The problem with these gases is that we use them in refrigerators and air conditioners, and we tend to hang on to those appliances for quite a few years, until they spring a leak, usually, and they no longer work. Now, if they spring a leak, where does the gas go? Into the atmosphere. When a serviceman has to service your equipment, or when you turn in your old air conditioner that's still working, whoever dismantles it has to remove and separate the freons. And they can then be disposed of properly, such as in a high temperature furnace. It will eventually break it down. That's one way. So there are ways to decompose these gases, but only if you can trap them. So they have what they call a blue bottle that is used by air conditioning service people to actually trap the gases so they don't escape into the atmosphere. Next. So why is the Earth only warmed up 1 degree? With all the extra greenhouse gases that we have, how come it hasn't gotten warmer? Well, we'll be talking about some of these things in the next lecture, but one of them is that the ocean itself is a huge volume. Roughly 3/4 of the Earth is covered with water, and the ocean is kilometers deep. That's an awful lot of water, which means it can absorb an awful lot of heat energy. Also, ice fields and glaciers. They also help to regulate the temperature. Just like an ice cube in your drink in the summertime will keep the drink cold as long as it hasn't melted totally. So while the ice is melting, it's absorbing heat. And then once it's changed its state completely to a liquid, then the temperature will rise. We refer to that as latent heat of freezing or melting. Latent heat means it's hidden heat. So to melt 1 gram of ice requires as much heat energy as warming 1 gram of water by 80 degrees. So from 0 to 80 is the same amount of heat energy as it takes to melt 1 gram of ice. And to melt or to boil or evaporate water requires a lot more energy yet. So when you get evaporation occurring at the surface of a body of water, that absorbs heat energy from the surroundings and cools it down. That's why trees are such good air conditioners, because you have water evaporating from the leaves on a sunny day, and that cools the surroundings. It keeps the leaves cool from getting so hot in the direct sun that the leaves will be destroyed, the tissues will be destroyed, but it also keeps the surroundings cool. So trees are excellent air conditioners, and they just do it naturally. Next. So what are some of these sinks for these greenhouse gases? We talk about sources and sinks in environmental science. a source is where it comes from, a sink is where it eventually goes. So with carbon dioxide, we have, of course, photosynthesis, and plant matter serves as a sink. So carbon dioxide is taken out through the process of photosynthesis, and the carbon is eventually stored then in plant tissue. Some of the carbon dioxide dissolves in the water, as we saw earlier in the presentation. And some of it is used to form carbonate rocks, limestone. Speaking of limestone, Lime Ridge Mall and Lime Ridge Street and Lime Kiln Road in Hamilton and Ancaster attest to the fact that there was a lot of limestone being mined in this area to make lime. So they had all these small lime kilns set up, which was then used to make the Portland cement. So there's a Lime Ridge, there's kind of a ridge that goes along the mountain, and there's a good quality limestone, which the early tradespeople used for making lime. Methane. The most important sink for methane is in the troposphere, which is the first layer of the atmosphere from about 0 to 16 kilometers up. We call that the troposphere. And there are very reactive molecules present in the atmosphere that can pluck off the hydrogen from the methane molecule, which then begins the decomposition of methane. Again, it's amazing how the creation has been structured to help take care of some of the stuff that goes in that we dump into the atmosphere. It's only when we put too much in that the atmosphere can't keep up. So the waste products or the byproducts from the decomposition is eventually carbon dioxide and water. You notice it's the same stuff you get as when you combust it or burn it. Except this occurs at the atmospheric temperatures involving a reactive species called hydroxyl radicals primarily. And next one. Nitrous oxide. It is actually pretty stable. And its major sink happens to be in the stratosphere, which is also where the ozone is. So the nitrous oxide can hang around for a long time because it is so stable, and it takes time for it to migrate into the stratosphere, where the UV light that is normally removed by ozone can also, in a sense, tear these molecules apart so that they become less reactive. Now, when you think of a jet flying up in the atmosphere, they're in the troposphere, usually just a couple of kilometers up, maybe 10 kilometers at most. They are then leaving nitrous oxide behind, which then can serve as a greenhouse gas. And it's not until that gets into the stratosphere that it will eventually get broken down. And then the last one, the halocarbons, what happens to them? Well, as we saw already earlier, the chlorofluorocarbons do not break down in the troposphere. And they're also not water soluble, so the rain doesn't wash them out of the atmosphere. And so slowly on, they drift into the stratosphere, where the intense UV radiation is capable of breaking a carbon-chlorine bond, which then begins the decomposition process of these compounds. The hydrofluorocarbons are a little bit more reactive because they have a hydrogen built into the molecule, and the hydroxyl radicals that are in the troposphere can grab onto that hydrogen and pull the hydrogen off, and that then becomes the start of the decomposition of the hydrofluorocarbons. There is some concern about some of the byproducts that you get. One of them is called trifluoroacetic acid. Acetic acid is normally two carbons, one of which has 3 hydrogens on it. And in the case of trifluoroacetic acid, the 3 hydrogens are replaced with fluorines. And so you have trifluoroacetic acid, and some organisms confuse the two and can take in the trifluoroacetic acid into its body, and we really don't know what the long-term health implications for that may be. So it's also one of the reasons then why we're looking at phasing out these compounds. Next. So, what are some of the future scenarios? This comes from the Intergovernmental Panel on Climate Change, the IPCC. And you hear quite a bit of that if you listen to some of the newscasts. The IPCC from the United Nations is often mentioned. It's the international body that tries to give advice in terms of climate change. And so they do, it's made up of a lot of scientists to gather all the data and try to put it into a form that can then be presented to the world leaders and to the public. So these are some scenarios. And these have to do with some of the models that they're working with. But basically, this one here says, so we're right about here right now. It says, if we really start to stop using fossil fuels right now, aggressively, there's a chance that we can follow this curve in terms of the carbon dioxide levels in the atmosphere. We have to start right now. Yesterday would have been better, but since that's already passed, today is a good time to start. And so we see that it actually will continue to rise for a while yet, before it eventually levels off, and then starts to go down. And notice this is projected to 2150. That's a long time into the future. But you can see that it doesn't go down very quickly. The Earth is going to be left with a relatively high level of carbon dioxide for many, many generations. The red line is another scenario where we start to reduce gradually, and then eventually, by the year 2050 or so, we're now at net zero carbon emissions. This one starts a little bit later, and it doesn't really do as much either. And this is the status quo. Keep on doing what we're doing. Keep on using the fossil fuels at our current rate, and this is the projected carbon dioxide level then. And I think, we could look at 2050. At 2050, this would be at 500 parts per million. Right now, we're at 410. And as I mentioned earlier, we're increasing about 3 parts per million. So 30 years, and we add another, 30 years of 3 parts per million would give us another 90 parts per million. Add that to the 410, and we're at 5. So this is the status quo, and I think more and more people are beginning to realize that the status quo is really not the direction we want to go.